So the trick to this one is that if this surface is truly frictionless and this person is exerting a force on the box, then Newton's third law says the box exerts a force on the person. There's no friction on their feet, nor is there friction under the box. So both objects begin to move. So I'm going to put in this force vector of 100 newtons. That's the force of the person pushing on the box. But we know when objects are interacting that the interaction forces point in opposite directions and have the same magnitude. So that box is pushing back on the person's hands, but I'll just attach to their body. They feel a force of 100 newtons. And then just so I don't have to refer up to that paragraph, I'm going to put in the 85 kilograms here and the 200 kilograms on the box. Okay, so other than that trickiness with Newton's third law, it's a pretty straightforward problem because I don't have any friction. Just each object just experiences a single force, so I can get their acceleration pretty quick. So the acceleration of the person, there's only one force, so I'm not even going to write F net. It's going to be F over m. 100 newtons over 85 kilograms. All right, so the way I've written this is a magnitude of an acceleration. If I put a vector hat over it, I would indicate direction with a minus sign. So I end up with 1.18. Again, maybe I'm only interested in the magnitude. If I wanted to do the vector acceleration really precisely, then I would say a vector is negative 1.18. All right, the box. It has more mass, so its acceleration should be less. So it feels a 100 Newton force, but it's 200 kilograms of mass, and that gives me 1/2 or 0.5 meters per second squared. And again, just for completeness, I could show the acceleration vector on here. It's smaller, and it's plus 0.5 meters per second squared. So that'd be a vector. Okay, so there's those, and then I want to do a little kinematics follow-up to this. So that's fair game on a lot of the dynamics problems that we do. You can combine them with kinematics. So we used Newton's laws, Newton's second and third laws to figure out the acceleration. But once you have the acceleration, you can start doing constant acceleration kinematics. So I want the final speed, assuming they started from rest. I even managed to say that in the setup this time. I want the final speed of the person and the final speed of the crate. So the person's going to be moving faster than the crate because it's a smaller mass and they've been accelerating faster. So we're assuming that this force stays constant and the acceleration stays constant because the force stays constant. So if you have a constant acceleration, you can just go back to this idea. Acceleration is the rate of change in velocity, so a change in velocity is given by acceleration times the change in time. Now I could write this formally as one of the kinematics equations. Maybe you'd rather think of it this way. It's just when I have a problem like this, I tend to go back to the more fundamental thing, but these are equivalent statements. In that kinematics formula, we assume that the initial time was t equals 0, so that really is a delta t there. So either way you slice it, I'm going to take the acceleration and multiply by how much time has gone by, and I've got the final velocity. All I wanted was the speed, so all I have to use is the magnitudes here. I don't care about plus and minus signs. So person v final, because v initial was 0, delta v is just v final. V final is equal to a times delta t, and that's going to be 1.18 meters per second squared times 0.5 seconds. We were told the push happened for 0.5 seconds. So that gives me 0.59 meters per second. All right, the box final speed is going to be acceleration for the box times how much time went by. So that's 0.5 meters per second squared times 0.5 seconds. So that gives me 0.25 meters per second. All right, so if they were truly on frictionless ice, this person pushes for half a second, and then they would both go sliding off, the person to the left, the box to the right, for infinity until they hit the edge of the frictionless plane, I guess.